All right. Good morning, everybody. Hopefully, everyone had a good weekend, and hope you had a chance to kind of rest a little bit. What I'd like to do today is I want to go ahead and I want to finish up with the discussion of these hybrid orbitals here. Now, like I had mentioned on Friday, this whole idea of hybridization is not an easy concept to kind of wrap your mind around. It first of all, it involves quantum mechanics again, where we were talking about orbitals and what they are. And then what we're doing on top of that then is that we're saying that these orbitals, these atomic orbitals, somehow they go ahead and they change and they become molecular orbitals when the atom then bonds with other atoms. And so, yet, what I would suggest you do then is, for the time being, don't worry about the fact that these orbitals are probability distribution. Don't even go into that direction. Don't even go there. Later on, when you take AP chemistry, AP physics, when you go on to higher level chemistry and higher level physics in college, for those of you who are heading in that direction, then you can start talking about and deal with these as being probability distributions again, because that's how I introduced orbitals back in chapter 5. What you should do here, in order to understand what hybridization is just imagine these orbitals then as being shapes. Imagine this being shapes, and that when the atomic orbitals come together to form new shapes, these new shapes are what we call then hybrid orbitals. Okay, so that's what you want to make sure you kind of keep in mind. And these shapes then, these new shapes then, these hybrid orbitals, they get together and they form then a three-dimensional structure that we will then be able to explore further, hopefully tomorrow when we start doing our PhET lab. Okay? But the goal then here is to try to understand what hybridization is, understand what hybrid orbitals are, and understand what hybrid orbitals do. Okay, and so that's what we're going to try to be, that's what we'll try to do in this particular discussion today, in this lesson today. And so by the end of this lesson, then hopefully we can start talking about bonding, what these hybrid orbitals do, and then we want to talk about molecular geometry. There's a three-dimensional shape that these hybrid orbitals take, and that we can use this to explain then the three-dimensional structures of these molecular compounds, and the three-dimensional structures of the compounds, of the structures that we drew in 2 dimensions last week. Okay. All right. So let me go ahead then, and let me go backwards here. Let me go and let's talk about the first type of hybridization that we encountered here. And let's talk about quickly review the sp3 hybrid orbitals. Okay. All right, so with the sp3 hybrid orbitals, these are orbitals that are created when an atom gets together and it forms a bond with another atom. What I want to make sure you understand then is that what we have here, and this is what I was trying to get at to you, and that is what we have on the left-hand side here. These orbitals here, these are atomic orbitals. Okay, these are orbitals that are found when the atom is all by itself. Okay, and we had used carbon as an example here. Okay, so carbon then, if we take a look at carbon, carbon has this electron configuration here. So we know then that, and I'm going to continue to use carbon as our example here. Okay, so carbon then has an electron configuration of 1s2, 2s2, and 2p2. And what we're focusing in on with the hybridization here are the s and the p orbitals here. Okay, so these are the atomic orbitals that we are looking at. The 1s orbital here, okay, that does not hybridize. The core electrons, that is the electrons closest to the nucleus, do not hybridize. The hybridization occurs only with the valence electrons, because remember then it's the valence electrons that are involved in bonding. And so when we talk about the hybridization then, the s orbital is this s orbital right here. That's the s orbital in the atomic state. Okay, so this is the s orbital, and it's this s orbital right there. And you can imagine then that there are two electrons in that s orbital, and I'm going to go ahead and draw that in right now. Okay, so you can imagine then that there are two electrons in that orbital. These two electrons here, that's one up and one down. Okay, so there are the two electrons there. Now, these electrons here, these orbitals here, these are the p orbitals that come from here. So the p orbitals and the s orbitals, these are from the 2s. So The number one here is just saying that one, remember with s orbitals, you only have one shape anyway. And it's that one shape and with that one s orbital that hybridizes together with all three of the p orbitals to form then these sp3 hybrid orbitals, which we'll get to in just a moment. Okay? But I want you to make sure you understand then that these electrons, these orbitals here, they contain the electrons, and I'm just going to draw them separately here. Okay, so there it is. There is the 2s orbital right there, okay? And these are the 2p orbitals. Okay? And remember, when we draw this and we write this out, the Lewis dot structure for atomic elemental carbon is going to be, there it is, there's the 2s pair, and there is the 2 lone pairs there. Okay? This is atomic. This is the elemental carbon. This is the carbon atom. Okay? When it's all by itself. Okay? Then what happens to carbon and what happens to many elements, many atoms, when they get together with other atoms, they undergo a process that we refer to as hybridization. They hybridize. And what they do when they hybridize is they take these they take these atomic orbitals and they blend them together. They mix them completely together. And if you notice here, what we see then is that when you get to on the right-hand side here, these are what we refer to as hybrid orbitals. So these are atomic orbitals here. What we have on the right-hand side, what we form then are the hybrid orbitals. Okay. Or because these are part of a molecule, we refer to, if these are atomic orbitals, we refer to these as molecular orbitals. And thus, molecular orbitals. Okay, so orbitals that are found in the molecule, these are orbitals found in the atom. Atomic versus molecular. That's what you got to make sure you keep in mind. I often refer to these more often. I more often refer to these orbitals as molecular orbitals. And so what you notice here then is with the formation of these new orbitals, these molecular orbitals here, what you notice is that it takes the atom takes a little bit of the p and mixes it together with a little bit of the s. Okay. And thus we call these new hybrid orbitals then, and when you have all of the p orbitals mixing with the s orbitals here. So if you notice that all of these orbitals are mixed together, okay, there's nothing left over here. Okay. When you mix it complete together, we refer to these as sp3 hybrid orbitals. Okay. So sp3 hybrid orbitals or sp3 molecular orbitals, and so that's what we have. And if you notice that we have 4 of them forming. Okay, we have 4 sp3, so you have to make sure you keep in mind then that this is referred to as sp3. So we have 1 sp3 hybrid orbital, we have another sp3 hybrid orbital, this is a third, and this is a fourth. Each one of these are referred to as sp3 hybrid orbitals. Okay? And if you notice that we have 4 of them, which corresponds to the 4 atomic orbitals that get together to form them. There's going to be that conservation that occurs. Okay? And so here you have 1 of the s orbital and 3 of the p orbitals. So that's a total of 4. So you have a total then when you combine together of 4 total orbitals, we end up with 4 total sp3 hybrid orbitals. Okay? And so that's what we have. That is what we refer to as sp3 hybridization. So that's what we have right there. So if you notice then these hybrid orbitals and this last picture here, they do not they are not situated in a 2-dimensional space. They are situated in a 3-dimensional space here. And so what we're going to see happening then, and this is what I want to make sure you understand, is that these 4 electrons then, because the sp3 hybrid orbitals are all what we refer to as degenerate. Okay? So when we talk about degeneracy, so these are degenerate. Okay? What we are saying then is that all these sp3 hybrid orbitals are equal in energy. And if they are equal in energy, remember what the reason why the 2 electrons here are sitting in the s orbital and these 2 spread out across the 2 p orbitals is because the s orbitals are slightly lower in energy than the p orbitals. The atomic s orbitals are slightly lower in energy than the p orbitals. And so what do, according to the Aufbau principle, what has to happen first? The lower energies has to fill in first before the higher energy orbitals have to fill in. Okay, and then according to Hund's rule, once these electrons here reach the higher orbitals, what they can do then is then they can spread out. So you can imagine then, if all of the molecular orbitals are equal in energy, then that is if they are degenerate, then according to Hund's rule, all the electrons can spread out. Okay, they can spread out so that now we have a single electron in each orbital. And that's why then when we take a look at molecular carbon and we draw the Lewis dot structure for molecular carbon, we show then that all four of those, I'm going to write here atomic carbon. Okay, that is the carbon atom. Okay. What we see then is that all four of those electrons are spread out, and so there are no pairs. And so when carbon becomes a molecular carbon, okay, when it becomes part of a molecule, the electron structure changes. The electron structure of the molecular carbon is different from the molecular of the atomic structure. I'm sorry, the structure of the molecular carbon is different from the structure of the atomic carbon. Atomic carbon, you have one pair, two unpairs. With the molecular carbon, you have four unpaired electrons. And what those electrons do is they sit in space along each one of these sp3 hybrid orbitals right there. Okay? And when the sp3 hybrid orbitals organize themselves in space, okay, and we will talk about why they do this, they're going to take this tetrahedral geometry. The best way to kind of imagine a tetrahedral is think about a tetrahedron. If you want to think about that, tetrahedron is kind of a pyramid-like structure almost, if you can imagine this, where we have three corners here, and then we have one corner on the top. Not quite pyramid. It's a little bit more than that. And that's why when we do the PhET lab tomorrow, it'll be much easier to identify and then be able to visualize the tetrahedral geometry. But just make sure you keep in mind then, now whenever you have sp3 hybrid orbitals, whenever you have sp3 hybridization, okay, you will always end up with the sp3 hybrid orbitals, assuming in a three-dimensional space, a geometry that we refer to as the tetrahedral geometry. Okay? All right. So that's what we covered on Friday. Okay, so please make sure you review if there's any part of this that you don't quite get. Okay, then please make sure you come by and see me and then get that extra help for this. But the sp3 hybrid orbitals is, I think, the easiest one to understand. Okay, all right, let's go ahead then and let's take a look at the remaining two types of hybrid orbitals. Okay. The next type of hybrid orbital is what I'm sorry. So there's sp3. They're all equal in energy. They're degenerate, so the four electrons spread out. Okay, and so for the most part, you're going to see then that sp3 hybridization will be involved in single bonding, and we'll talk about that in just in a little bit. Okay, all right. Let's take a look then at sp2 hybridization here. So let's go ahead and let's analyze what we have here. And again, I'm going to use carbon as our example. So I'm going to go ahead and write out the structure, electron configuration of carbon up here. So we have then 1s2, 2s2, 2p2, and this is our 2s orbital right here. So let's make sure you keep that in mind. This is the 2s orbital right here, and these here are the three 2p orbitals. So that's the 2s orbital here and the 2p orbitals here. So we have two electrons in the 2s orbital, okay, and we have two electrons in the 2p orbitals here. Okay. All right, so these are the atomic, or again, these are the atoms. These are the atomic orbitals here. Okay, so we're going to take the atomic orbitals, and what carbon does, depending on what it bonds with, okay, when it hybridizes, it can hybridize to form sp3 hybrid orbitals, or it can hybridize, again, it depends on what other carbon, what other atom it attaches to. But this elemental carbon right here, this carbon atom, okay, will hybridize and form what are called sp2 hybrid orbitals. Okay? And so if you notice here, this is where we left off with on Friday, okay, with sp2 hybridization, there are only three, there are only three sp2. Now you got to be careful with this here, folks. We have four sp3 hybrid orbitals. Okay? We have three sp2 hybrid orbitals. Let's go ahead and let's take a look at how these three hybrid orbitals here. So we have then three sp2. Each one of these then will be a hybrid orbital. So if you notice then, what we've done then is with sp2 hybridization, we've taken two of the atomic orbitals, two of these p orbitals right here, taking two of those, and we mix them together. We hybridize them with one. sp with the s orbital, and that's where we get there. So we got a little bit s, and we have two of the 2p orbitals that are hybridizing here to form then 3 total sp2 hybrid orbitals. So let's go ahead and write that in. We have then an sp2 hybrid orbital here. We have a second sp2 hybrid orbital, and we have a third sp2 hybrid orbital. Okay, so we're taking two of these two of the p orbitals and hybridizing it with an s orbital. So we end up with 3. Again, like I said, conservation has to occur here. We have 3 sp2 hybrid orbitals. Okay, so 1 plus 2 equals 3. So that's what we have there. Then we have then 1 p orbital here that remains completely unchanged. Okay, nothing happens to that p orbital. Nothing happens to that p orbital. It stays unchanged. Okay, so with that said, where do these 4 electrons go now? So remember, once we hybridize, okay, 3 of them will go into the sp2 hybrid orbitals, and the last one will fall into this unhybridized p orbital here. So this is still, so these are, so what we have here then are, we will have 3 molecular orbitals. So these are 3 molecular orbitals here. So these are molecular orbitals. And we have 1 left over. We have 1 atomic orbital still unchanged. So for sp2, so this is an atomic orbital. We still have 1 atomic orbital left over that has not changed it, and it is part of the molecule. And so with sp3 hybridization, we had no atomic orbitals. Every one of the orbitals were molecular orbitals. With sp2 hybridization, we have 3 molecular orbitals and 1 atomic orbital here. Okay. Now, with that said, then the electrons will still spread out. Make sure you understand that. If we draw the Lewis dot structure for this, if we draw the Lewis dot structure for this carbon here, okay, it's still going to look like this. We have 4 separate carbon electrons. Okay, we have 4 electrons here. The main difference now is this. One of those electrons, and I'm going to highlight this in a different color. Okay, I'm going to highlight this, let's say in purple, since we already have here. Okay, so one of these electrons here, the one in purple right there, is going to be higher in energy than these 3 here. So these 3 hybrid orbitals here, the molecular orbitals, these are degenerate. These 3 are degenerate. This here is not degenerate, meaning then that it is not equal in energy. So if you take a look, if you can kind of imagine this here, okay, and I'll point this out to you again in just a moment. Okay. The 3 sp2 orbitals here, and we talked about energy, okay, and I'm just going to draw it down here really quickly. Okay, so we have energy going up here, so energy is moving up, so energy increases. So this is energy. If energy increases here, what we're going to see then is that we're going to see then that the 3 degenerate orbitals, oh, excuse me. Oh, excuse me. Okay, so we have then the hybrid orbitals down here. So these are the 3 sp2 hybrid orbitals. And then we have then the atomic orbital, the unhybridized atomic orbital just right there, just slightly above. Okay. And so I'm going to draw this then as boxes real quickly. Okay, so we have then 1, 2, 3. And these are the sp2 hybrid orbitals. Remember, we just talked about. So this is the sp2 hybrid orbitals. And then we have 1 box up here that represents then the p orbital. So here it is. This is the p orbital right there. Okay. This is the unhybridized p orbital that has done nothing. So this is the p orbital right there. And the electrons then will fall in line, just like we showed here, with these 3 equal in energy. And this last one here in the p orbital, a little bit higher in energy. Okay, and so that's what we see here. So there it is. So in 3 dimensions, then we're going to see then that we have 1 electron here, 2nd electron here, and a 3rd electron here. These are the sp2 hybrid orbitals, and we have 1 electron in the p orbital that again is higher in energy, and that's what you want to make sure you keep in mind. The electron in the p orbital is higher in energy. Okay, and so let me point this out to you again, and you need to make sure you keep this in mind. That is higher in energy. higher energy. Oh, sorry. Maybe get that a little bit closer. So this, the one purple electron there is going to be higher in energy, higher energy. Okay, and the remaining three are degenerate. So we have 1, 2, and 3. Those are going to be degenerate, equal in energy. And that is what you really need to make sure you keep in mind. Okay. All right. So with that said, then when atomic carbon hybridizes to form molecular carbon, and it hybridizes in an sp2 manner, it's going to form 3 sp2 hybrid orbitals that are all degenerate, equal in energy, and it's going to leave one atomic p orbital, one of the atomic orbitals, which is a p orbital, unhybridized, and that in which an electron is going to sit, and it's going to be higher in energy than the 3 hybridized molecular orbitals. Okay. All right, so that's sp2 hybridization, guys. That is sp2 hybridization, and make sure you understand then how it is similar to the sp3 hybridization and how it's different. Okay, and make sure you are able to deal with the similarities and differences as well. Okay. All right, so with that said then, let's go ahead and let me just quickly wrap up here. Make sure you understand then that when the sp2 hybrid orbitals form, then we're going to have then 3 sp2 hybrid orbitals and 1 unhybridized orbital here. Then again, the electrons will spread out. Remember, the 1s orbitals, they don't do anything. Nothing happens to those. And so therefore then, even though it's a little bit, I don't show this here, remember, it's this orbital here, this electron here that is higher in energy, okay, higher in energy than these 3 here. Okay, so make sure you keep this in mind. Now, we typically see then sp2 hybrid orbitals form with double bonds. So sp3 hybrid orbitals always going to be involved in single bonding. sp2 hybrid orbitals are going to be involved in double bonds. And that's what you want to make sure you keep in mind as we go forward with this. Okay, so this is going to help you understand why we're doing this. Okay, so sp2 hybridization is important in understanding double bonds. sp3 hybridization is going to be important in understanding single bonds. Okay, and so that's what we're going to be doing. That's what we're going to be doing with this hybridization here. Is we're going to try to understand how these covalent bonds, the different types of covalent bonds form. Okay, so with that said, then you can imagine if sp3 is responsible for single bonds, that's how single bonds form. Okay? And if sp2 hybridization is responsible for double bonding, then we must have one last type of hybridization that we need to discuss in order to understand how triple bonds form. And triple bonds form as a result of carbon undergoing then a hybridization, a different type of hybridization here. And let's go ahead and take a look at it. Okay, let's talk about this. Good. And again, I'm going to go ahead and write out the so I do this here. Let's write out the electron configuration for carbon again. So carbon is 1s2, 2s2, 2p2. Okay, so again, we have here the atomic orbitals. Let's go ahead and write those out here. So here again, label those. These are the atomic orbitals. Okay, that is the orbitals that exist when the carbon atom is an atom, orbitals. Okay. And the Lewis dot structure for this again, and I hate to be so redundant, but I want to make sure that I really hammer home this point, the difference then between atomic and molecular. Okay, so the orbitals are going to be different. Okay, so we have then atomic carbon here. Okay. All right, let's take a look at this then. So we have our 2s orbital here. So this is our 2s orbital. Okay, and then we have then here our 2 p orbitals here. Okay, all right. So we have then the 4 electrons. Let's go and put them in here. We have 2 in the 2s orbital, and I'm going to write these down here. 2 in the 2p orbitals here. Okay, all right. And so let's take a look at what happens when we form sp hybridization. If you take a look at this one, then you're going to see then that when sp hybridization occurs, the atom takes the s orbital and it hybridizes it with only one of the p orbitals to form then 2 sp orbitals. Okay, so we have here then sp orbital, an sp orbital here, sp, sorry, and an sp orbital here. Okay, and so if you not, so again, if the conservation occurs, we have two orbitals mixing together, they hybridize, and they form two hybrid orbitals. These hybrid orbitals now are referred to as sp hybrid orbitals because we're taking one s and one p and we're hybridizing them together. And that's essentially what the nomenclature means here. Okay? Whereas with sp2, we saw then one s and two p orbitals hybridizing, and with sp3, we saw one s and all three of them. And that should help you also understand then what type of hybrid orbitals form here. Okay, so here then we have the molecular orbitals. We have two molecular orbitals. Okay, so we have then the molecular orbitals here forming. And as you notice here, we have two atomic orbitals that are unchanged. Okay, so we have two atomic orbitals, two molecular orbitals forming when we we hybridize by sp hybridization. Okay, so make sure you understand that only with sp3, do we have all of the atomic orbitals hybridizing. So we have none of them left over. With sp2 and with sp, we're going to have hybrid or atomic orbitals left over. Okay. All right. So with that said, then let's see how the electrons spread out. Okay, so we have the 4 electrons here. They're going to spread out so that we have 2 electrons in the hybrid sp hybrid orbitals, and we're going to have 2 electrons in the unhybridized p orbitals. So again, these are going to be degenerate. That means these are going to be equal in energy to each other, and these here are going to be both. They will be degenerate, but they will not be equal in energy to these p-sp orbitals here. So if we take a look at then at the energy diagram again really quickly. Okay, so let's take a look at the energy diagram here. Okay. And so with that said, energy is increasing again as we go up. Okay, so we have increasing energy. Okay, all right. So what we're going to see then is we're going to see that the sp hybrid orbitals then are going to be slightly lower in energy. So both of those will be down here. So we have sp there, and the two p orbitals are going to be a little bit higher in energy up here. So they are not degenerate with the hybrid orbitals, but they are degenerate with each other. So we draw in our boxes then. Okay? So there's one sp2, there's a second sp2. Okay, and these here are the p orbitals right there. Okay, we're going to see then that these 2 electrons here will be lower in energy. Okay, because these are the sp orbitals. Okay, and these are the unhybridized p orbitals here. Okay, and if you notice, they are higher in energy than the sp, but they are equal in energy to each other. Okay? And so when we take a look at the carbon atom, we write out the Lewis dot structure for the carbon atom. Okay, we're going to now have two electrons that are equal in energy to each other. Those are the hybridized, and then we're going to have 2 electrons that are going to be also equal in energy to each other, but they're going to be higher in energy than the 2 here. Okay, so that's what you want to make sure you keep in mind. Okay? And so the electrons then will fit in. We're going to have 2 electrons in the hybrid orbitals here, and then we're going to have 2 electrons, one in one of these p orbitals. That's one p orbital here, and we have another p orbital here. Okay, and so we form then this what's called the linear geometry. And what you're going to notice then is that with the sp hybrid orbitals, what we're going to see happening is that these are responsible. These will form when the carbon or any atom wants to form a triple bond. Okay, so that's what we see there. So let's go ahead and take a look at the sp orbital. Okay, all right. So the sp orbital then, okay, an s and the 2 p orbitals here they form, and here it is. I showed you the energy. Then the 2 sp hybrid electron, 2 electrons in the sp, and this is sp by the way. I'm sorry, there's a typo here. This is sp orbital here, but we have 2 of them. Okay, and let me just make sure I address that. Okay, so I'm sorry, this is not sp2 hybridization. That's a typo right there. So real quick. Ignore that 2. That 2 doesn't belong there. So we have 2 sp hybridization and 2 sp hybrid orbitals and 2 p orbitals that are unhybridized. Okay? And we have 2 electrons in each. These 2 hybrid orbitals here contain electrons that are lower in energy. These 2 unhybridized p orbitals contain electrons that are going to be higher in energy. But if you notice them, these 2 electrons are degenerate with each other, and these 2 electrons are in turn also degenerate with each other. But the hybrid orbital electrons and the p orbital electrons are not degenerate with each other. Okay, they are different. They have different energy. Okay. All right. So with that said, then the sp orbital then is we see that forming when we have a triple bond forming. Okay. All right. Let's go ahead then and before we get into seeing how these orbitals are involved in bonding, let's talk about then what actually happens with these orbitals when they do form the bond. Okay, so they have to interact with one another, and so we got to make sure then that we understand that that interaction has to occur in order for the bonding to form. Okay, all right. So the first type of interaction that we're going to talk about here is what's called sigma bonding interaction. Okay, so whenever you have a sigma bonding interaction, okay, we have then 2 orbitals. Okay, and in this case here, I show you s orbitals here, but this will also be true with hybrid orbitals as well. Okay, what happens then is that these 2 orbitals, then when they align, and the best way I can get you to see this is that you have 2 orbitals there. I'm going to take 2 pens to show you. Okay, they align so that they are when they come together, you can draw a straight line through them. Okay, so if you notice that these are the 2 orbitals here. Hopefully you can see this. I don't know if you can see this. Okay, there it is. So the 2 pens there, and let me close here. That doesn't work too well. I think the screen's okay. So hopefully you can see this. So you can imagine then I have my 2 pens here. Okay, they're going to come together. Okay, and if you notice then as they come together, they meet. They form a straight line. There is a straight line that you can draw from end to end on this here. Whenever you have that type of interaction between 2 different orbitals, we refer to that as sigma bonding interaction. Okay, that's a sigma bond. And let me go ahead and draw this in. Okay, so this is what we refer to then as a sigma bonding interaction. Okay. Sigma for more to be more precise. So sigma bonding interaction. And when they interact with each other in this manner here, like I said, when they do interact and they blend, what you can do there is you can draw a line, a straight line through, and it's a line of symmetry that you can draw straight through there. Okay, and so then therefore, if you could do that, okay, you have then a sigma bonding interaction. Okay, so we have then a line of symmetry, okay, that you can draw through this one, and so you want to make sure then that if you can identify that, we have then what's called a sigma bonding interaction. Okay, symmetrical molecular orbitals, okay, and then you can have a symmetrical a line of symmetry around the nucleus of both of those axes. Okay, so that is what we refer to as the sigma bonding interaction. Now, there's a second type of interaction here that we can we need to talk about. Okay, so orbitals can interact in a sigma bonding interaction, but they can also interact in what we refer to as a pi bonding. What we refer to then as a pi bonding interaction as well. Okay. All right. So so I'm sorry. This is another example of a sigma bonding interaction. This is an example of a sigma bonding interaction involving 2 atomic s orbitals. This is a sigma bonding interaction involving sp hybrid orbitals. Okay, it could be sp, sp3, or sp2 hybrid orbitals. And what you're going to see then is they get together. Okay, they blend together. Don't worry about the positive and negative signs here for right now. That's something that you will see later on. Okay, but this, so the way that we interact with these p orbitals here, you can also imagine that the hybrid orbitals acting in the same way. So they come together. Okay, and again, you can draw a line of symmetry through this interaction here. Okay, so let's go ahead and do that really quickly. So when these 2 p orbitals interact with one another, you can draw a straight line of symmetry through them. The same on both sides. Okay, so you can imagine this can also account for how molecular orbitals will interact with one another, and that's exactly what we see also with the molecular orbitals as well. Okay, so sigma bonds can form both at the atomic with atomic orbitals and with sigma with hybrid orbitals as well. Okay. All right. Let's go ahead then and let's talk about the second type of bonding interaction, which are the pi bonding interactions. Okay. So going back to my pens, okay, if you can imagine this here, the 2 pens here, that's the sigma bonding interaction. They are lined up. Okay, with the pi bonding interactions here, what we see then is that they line up so that they are parallel to one another. They don't make a line, but the two bonds, the two orbitals, what they do then is they line up so that they are side by side with one another. They sit side by side with one another, and that's what we see here with these two orbitals here. Okay, so we have two p orbitals here. Again, I'm going to use the atomic orbitals here, and I'm going to try to finish up this really quickly. They line up, they are in a line with one another. Okay, so they're facing the same way. And when they blend together, then you can draw a line of symmetry, I suppose. But the idea then is that these two orbitals here, they line up, so they are side by side with one another. And when you have that side by side interaction, then okay, you're going to have more. You're going to have that side by side interaction. That's what we refer to then as the pi bonding interaction. Okay. And so this pi bonding interaction here is a weaker interaction than the sigma bonding interaction, but it is important in forming then what we call these. It's important in forming the double bonds and the triple bonds, and that's what we will talk about tomorrow when we continue this discussion. So what we'll do then is I'll finish up with this discussion tomorrow. I will talk about then the Vesper theory, and then hopefully on Thursday you can apply what we learned tomorrow and I'll use the FET tomorrow, by the way, to get this help you to see this. But then on Thursday I'll post the FET for you, and we'll spend Thursday working on the FET. Okay. All right, very good, folks. Have a good rest of your day, and I will see you folks I'll see you in class tomorrow. Okay. All right. Have a good day, folks, and I'll see you tomorrow.